Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our linear algebra series, and we're just going to be continuing talking about inverses. Okay. So last time we ended up with doing a proof of how we can prove if, let's say, we have some linear transformation, we can prove that there is an inverse of that p. There's an inverse, and that inverse is a linear transformation. So we say that P has only an inverse if M is N, and it's invertible if that P is also a linear transformation. So we proved A, that if it's one-to-one, it's N greater than or equal to M. And if that P is also onto, it's also N greater than or equal to M. And so the only way for T to be one-to-one and onto is if they're equal. Okay? Why not greater? Because it says so here. There won't be an inverse if they are not equal. So if n was greater than m, there won't be an inverse, but we want there to be an inverse. Okay. And then we let y sub 1 and y sub 2. So here we basically prove that when we get the inverse, and then we translate that, and at the end, this is the first definition or first property of what it means to have a linear transformation, and so we see that there is. Okay. All right, now we're going to continue. Oh yeah, we can also prove this using the scalar one, but I'm not going to do that today. Okay, so note that having m equals n does not guarantee that t will have an inverse. It only means that there is a possibility that t will have an inverse, but if they are not equal, then we know that it's guaranteed that they won't. But when they're equal, it doesn't guarantee that they have. There's just the possibility that it will have. Okay, so I'm saying here is that, and we have to note it. So let's note that m equals to n does not guarantee the inverse. Let's do an example. So if A has these entries and we say this T inverse is the same as the matvec, and let's say that the inverse is also going to be a matvec. Let's do B matrix. We could do any, to be honest. What else can we say? We say that M and N are equal, right? So we're going to say that T is a transformation from Rn, which is going to be 2. It's going to transform our vector into an R2. I think it's just going to have different components, but it's not, it's transformed. But we say here that this transformation does not have an inverse, or it's not invertible. Why? I don't know. Let's check. Let's check our definitions of what it means to have an inverse or it's invertible. T is one-to-one and onto. Is T one-to-one and onto? Well, it's one-to-one. N is greater than or equal to M, right? That's what we know about one-to-one. And same thing for onto. Are these ST a one-to-one and onto linear transformation? R2 to R2. Well, from the first idea where N is equal to M, yes. So they are from that aspect. What else can we say? If they're one-to-one, or if they're even onto. Is this thing one-to-one and onto? This AX? What can we say? Well, we could try it out, right? We could say that this AX is gonna be what? These guys, right? Which is the same thing as x sub 1 plus 2x sub 2, 3x sub 1 plus 6x sub 2. This is the same thing as the linear transformation. Now, what can we say? I can't think of anything yet. Can we try and look at the pivots, maybe? Let's try. We do 3, 6. Oh, look at that. 0, 0. There is no pivot in every row. And if there is no pivot every row, oh, there's also no pivot every column. This column here has a pivot. Does this column here have a pivot? No. We have one free variable. If there's no pivot every row, it's not onto. If there's no pivot every function, every column, it's not one-to-one. So we're really just memorizing ideas here. It says so. Where did it say that? Here. There's a pivot every row, T is onto. If there's a pivot every column, T is one-to-one. Now, is there? Is there a pivot every column? No. So it's not one-to-one. Is there a pivot every row? No, it doesn't. So we say that this transformation, this T, is not invertible since it's not one-to-one nor onto. So that means if it's not one-to-one and onto, or what's that? It's none of these, so it's not invertible. There is no inverse. Okay? That's the idea. So we're really just connecting ideas together. Okay, let me keep going. So, okay, but here's the idea. We say, okay, we have an n Rn to Rn. If this thing is indeed an invertible linear transformation, then what? Then we say it's inverse, which goes from this Rn back to this Rn. So we say that Rn back to Rn. That thing, the inverse, is also a linear transformation. Okay? And so there exists, so there exists A, B, and these are n by n matrices, so they're square matrices, such that this T of x is the same thing as A times X, and the inverse of that input vector X is also inverse. No, not B inverse. My bad. It's also BX. Okay. Furthermore, for each X in Rn, we have the following. We have X is equal to T inverse X. This thing is equal to, so we can translate that to T bx, and we can translate this to A B. Since ABX is just equal to X for all X in Rn, we say that this AB is actually just the identity matrix. So now we're getting into it. So a matrix, here's the idea. A matrix can be invertible. Okay. All right, let's do another definition here. So we say that an n by n matrix A is invertible if there exists a matrix B that's also n by n. So they're both square matrices such that the product of AB is just the identity at n. So a matrix A is invertible precisely when the associated linear transformation. Let me just read that. Oh, when the associated linear transformation is invertible. So we say that a matrix A is invertible precisely when that T inverse is equal to that mat vec, when we say that that transformation is invertible. So it's nice how we can kind of build off of ideas that we already have, even though I tend to forget what those ideas are, but it's just nice to have ideas that we can just build straight up of. Okay, let's do an example. We're gonna let A be a 3x3 matrix with these entries 1, 2, 1, 2, 5, 2, -1, -1, 0. And we let B be another matrix. So we say 2, -2, 3, -1, 1, -1, -1, 0, 1. Okay. We're gonna prove A is invertible by showing that when we multiply AB, it's going to be the identity matrix. Did we show identity matrix in this course? I don't think we did yet. I tend to forget. In this case, it's I3, I sub 3. Anyway, I forgot. I probably talked about it at some point. So remember when we're multiplying matrices together, we're just doing, did we talk about it in this course? No, I forgot. Because I was so focused on the applied linear algebra one. Anyway, I'll just bring it here. It's interchangeable anyway, but the idea is we can use dot products. We can think of it as just multiplying a matrix by a vector, or there's probably another way of doing it. Some use a computer, but if we solve this, we're going to get this resulting matrix, which is just the identity with three entries of one in the diagonal. That's what that three means. It's just the dimensions. Okay. I don't even think we talked about permutation matrix here. I just forgot. Anyway, so we have that. And so we say A is invertible, or it has an inverse. And the funny thing is that B is the inverse. This is the inverse of this. And there is a way to get from A to B. And we're going to find that out. Okay. And we know that from section 3.2 that sometimes when we multiply A by B, that's not equal to multiplying B by A. So order matters. But if we multiply A, B, and let's say they are inverses of each other, that's just going to result in identity. And that's the same thing for B and A. Okay. So we say in general, AB is not the same as BA. But if A and B are square, we say they are square matrices. Once they're square and their product, AB, is just the identity IN, then BA is equal to AB is equal to IN. Those three tend to be the same things. Okay. Let's go through another theorem here. Let's see this one. So here we suppose A is invertible. So what does that mean? We say that BA is IN and B the matrix B such that AB equals BA equals IN. This matrix B is unique. What does it mean for it to be unique? We'll find out. We'll know what that definition is. Now, there is a proof of this idea. That's fine. I'll go through the proof. So we let, oh, okay. So we let these matrices be in Rn. Now, since AB is IN, we have, let's say, AB times this matvec, which is the same thing as the identity times the matvec, which is the same thing as the matvec. And then we say A, BAX, which is the same thing as AX. What are we noticing? And then this is the same thing as, say we have A BAX minus X, which is a 0. We'll look at it here. Now, since A is invertible, AY is equal to 0. And this thing has only one trivial solution. Since the corresponding linear transformation, so we're always going to base this off back to the linear transformation. This thing is a 1-to-1. Hence, we say that A, BA, X minus X equals 0 implies the following. This BA X minus X is a 0. We can just rewrite it as BAX equals X. Oh, we're just proving the theorem. Okay. And since BA X equals X for all X, so I'm using a lot more notation now. NRN, conclude BA is just identity, NN. And to show that B is unique, so that was that part. If we want to say that that is unique, suppose there's another matrix. So we say C is an n by n. Such that, so we prove this part. Then we have the following. We have B, AB, which is equal to BAC. And then what happens here? BA, B. So this is one of the properties of a matrix. BAC. This tells us B is C. And why does this work? Because B B is just the identity. And since B equals C, so it's really just a one-to-one. That's what it means to be unique. Cool. That's how we do a proof. Okay. Let's do a new definition here. Two point 24. Now we're going to talk about an inverse matrix. So if, let's say we have a matrix n by n, and we say this thing is invertible. Now we have a new thing to call it. A with the power of -1 is inverse of A. Oh, I forgot to say. Based off of the definitions we have, this is also an n by n. And so based off of this idea, yes, this is a unique n by n matrix. So we say that this thing is a unique matrix. And we say that A inverse is just the same as A inverse A, which is the same as the identity at n. Okay? Okay, we actually have a couple more here. Huh. Okay, yeah, we have a couple more stuff to go through. Actually, not too much anymore. It should be pretty quick. Because that's mostly about finding examples. Okay, let's talk some buzzwords. Non-singular and singular. I have no idea what these are. The first time I'm going to look at this. So we say that a square matrix A is invertible. Oh, we call that non-singular. But if it doesn't have an inverse, it's singular. Oh, I see. Okay, it's a really simple idea. We say that a matrix A that is invertible is non-singular. A matrix A, or these are both square, I forgot to say. That doesn't have inverse is singular. So we kind of, this is, okay, this is actually pretty self-explanatory. Let's just say, suppose A is a square matrix n by n. Okay, so it's invertible, meaning it's non-singular, but if it's not invertible, it's singular. Okay, and we have another theorem here, which I think is pretty annoying. Not really. It's just annoying that we have so many theorems. This next theorem gives several important properties of invertible matrices, and we note the distinction between C and D of that theorem, and those given in another theorem that we've discussed, which of course I forgot. I can't memorize theorems. Props to people who can. Good job. Okay, we have theorem 3.25. How many theorems are these here? Here we let A and B, and let's say they are non-singular. Or another case, in other words, they're invertible. And they are n by n matrices. And C and D, I'm assuming C and D are also n by m. Oh no, n by m. So these guys are different. And then we have the following. So we say, okay, for letter A inverse is invertible if when we get we have its inverse, we get that inverse, it's back to A. All right. B, AB is invertible. So I'm thinking the resulting matrix product of AB is invertible if we have this AB inverse. And we say that, okay, this one's interesting. B inverse multiplied by A inverse. And remember how when we do matrices, order matters? Here they put the B first multiplied by the A inverse next. So of course, we're going to write proofs on these to check if they're possible. And then if we say we have AC is equal to AD, that's the same thing as C. This one's a bit more like something we know, CD. Then lastly, if AC is equal to 0, what happens when we multiply AC? C is an n by n, A is an n by n. So we're going to say n, m, because C has m columns. M as in me. Then C is that same matrix, 0 and m. Right, so I'm going to take a little break. I'll see you guys in the next video where I'm going to show a proof about this, and we'll continue on with other topics that we have to discuss in this section. See you guys.